sensors that they are prototyping. So today they are going to present new wearable interaction sensors and also their company and the research that is going on in Milano in their laboratory. So I'm very pleased to present to you Engineer Paolo Belluco. He is PhD and founder of LWT3 company. Samuele Polissina, a designer and also founder of LWT3. And we have also two master students from the University Polytechnic of Milano, Roberto D'Alessandri and Davide Liotti. They are doing an internship, they are finishing an internship at LWT3, almost finished, yes. At LWT3. So I give the floor to LWT3.
Thank you very much. First of all, thank you for the invitation by Giusy, class, and Lumut, and thank you to see our presentation. In very few words, we are a small company in Italy, based on Milan, and we are not musicians. We are engineers and designers. I was probably the worst piano player in the world, so I decided to move to engineer. And we are involved in a lot of different projects. We work with industry, with services, with sportsmen, and we make a lot of things about Internet of Things, about data. Where is the data? We go and try to capture and get the information. After some years of working in IoT environment, working with sensors, a lot of sensors, and working with data, we met Giusy, and we decided to start using it, the same technology, the same skills, the same ability to build something that is able to get our data from the environment in order to retrieve information for musicians, for performative artists. So, in very few words, we are involved in three big pillars, very far at the first sight, one for another one, but the layer, the glue that connects everything, from our point of view, is the data layer. So, we moved from the field, from the part of the field that produce data, where the data source are, and we move to elaboration and visualization. But the same core skill set that you use for industry, for example, we worked in a gallery, okay, in a cave with miners, we work for Lamborghini, so for different, very different type of customers, and now we know that probably sportsmen or worker or musician are the same, are humans. So the humans moved, okay? The humans produce signals, and if you are a piano player, you are a minus, for us it's the same, okay? Because you're producing materials, you're producing information. And we work in the same way for miners, piano player, etc. We work from field to the visualization. In other words, we try to be full stack on data, and we are able to extract information from data source, okay? Or we are able to build, we have tried to build devices that is able to create the source of the data. And we try to manage this pipeline until the visualization or the utilization of the information itself. For our point of view, I'm a computer science engineering. It's very important to look at the managed storage part, because now we are always talking about one or two people and very few persons and very few data. But now we have to face to a lot of data, a huge amount of data. Because now we have, for example, try to extract information just from one person. Okay, we start, for example, with EMG, ENG, and other bunch of sensors, a lot of megabytes in a sequence of data, if you want to capture even only the raw data. So it's important to pass to the mindset of big data, okay, for us, in order to extract information and try to find out patterns and everything you want from information itself. And I don't want to steal more time from my colleagues because there are a lot of very interesting things to show. Just to have an idea, we have a lab, we have a lot of skill, but for us it's important to have not only the right R&D skills to build the system, to build the devices, is needed to build a new type of interaction system. As I said, always in a lot of different places. For us, JUSE is like the Rosetta Stone for us, because it's the Rosetta Stone, because it is able to capture the information from musician and apply to the engineers in order to have the same jargon. Okay. Just to make a very speed and fast use cases, we work with aerospace. We work, for example, we put EMG, metabolic sensor, and motion capture on helicopter simulation in order to find out the differences between the simulation and the real pilot environment, which is the metabolic or the muscle strain differences between a very real simulation and the reality. So we try to find out the differences. And we work for the wearable computer is the device that we will show after. And I want to put the last thing I want to put the focus on is about the sportsman. So for our experience, professional sportsmen and musicians are almost the same thing. Okay, they want their performances. Okay, the only difference is the KPI. So the runner wants to win the race, and the artist want to be the best. Okay, but for our point of view, even from the point of view of the, for example, metabolic biomechanics, the optimization of the movement, okay, the optimization of the performance, the economy of the movement is almost the same thing. So we shall try to treat the same, the humans, the same thing, and so we use the same technology that we will show now to retrieve information from, as I said before, sportsmen, workers, and so on. Just to say, we are trying to build the hammer and the anvil, but obviously the artist is the blacksmith. Now I pass the words to Samuele Polistina. Thank you very much.
So, my part, thanks for the introduction of my colleague and the co-founder and the people that, because we started really in the past, not a few years ago, but more than 10 years ago, working together and making some research. But we are the one part and the other part of the moon. I'm a designer, he is an engineer. So we fight together, discussing about projects always, and my opinion is different from his opinion, and sometimes some of us fail on this fight. But the thing is that we always recreate something, or we thinking about this opportunity to grow up together. Now, why we are here? Because we, as Paolo told us, that thanks to our Rosetta Stone, we start in this field about some project related to the arts and tech. But the data layer is the same. So this data layer is composed by 3 different, in this case are hexagon, but are harvesting, elaboration, and visualization. My work is at the end of the part, the visualization, because I'm a designer, I'm not an engineer, but I also have the vocabulary to talk with engineer and other professional. What about the harvesting? For in this field, for the art, we use some of our sensors. We usually use these sensors, IoT sensors or EMG sensor, because our king signals are the SEMG, so electromyography, surface electromyography. So we can acquire muscles, superficial muscles activities, but not the deeper one, because you need to put needles on it, and sometimes the artists are not comfortable on this. And also we use also other IoT sensor like BLE sensors, Bluetooth sensors that we can reconfigure from different other projects, for example in the safety health project. And we can use, we thought that was interesting also to use in the project with the artist. So during COVID, also the lab was empty because the athletes can come to our sports lab, and we'll start to make some experimental with. Also, is present here. I don't know, so it's here. It's outside. The violinist Simonetta Sargenti. And to acquire we made some acquisition of his during performing the violin, so playing the violin, and we carry on to understand what about the protocols, because protocols for us it's important when we work with other fields, but also for artists. And also we need, if we talk about the last part of visualization, we have two choices. We can use the data, we can analyze all the data in post-production offline with offline data, or we can use the data in real time, so to make a performance. And for doing this, we have some protocols and some methodology to follow. About our expertise, that we have a human-machine interface lab that we can reconfigure about the task, and also we have of course, if you saw in the other presentation, it's not like a IPEM lab that is a huge lab and fantastic with full of technologies. We have the small version of that lab that works quite nice for us, and because also we are not an institution or a university. We are a small university, like a small university, really small university, because of course we were a researcher in the university. So also our methodology is that one, that we move in a company, and we can reconfigure our lab to make the acquisition of all the biometrics, and the things that we can do compared to the other project that we saw today, or I didn't saw any project before. We can make all this data together, so we can make the data fusion of all the data. And the nice thing is that we have the property board, EMG property board, and we also develop the hardware and software, and we can manage really well these devices. And also we can add some features and functionality to our system. To doing that, also we have inside in our company some labs. So we mixed design and engineering together, and we are able to make digital and physical, create a physical and digital object. What it means that if we want to make a prototype, for example, a suit, a complete suit sensorized, we are able to do a digital fabrication inside our lab. So we have a fashion designer, we have the high-end computer to doing that, we have the physical mannequin, we can make the cut and sew model with all the sensor embedded on it. And of course we can also manage about the electronics, so we can print the cases, also the outside cases, so we can make a prototype, full functioning prototype. This is really, really nice. What about also what we can do for in this field arts? We can collaborate, and so in these 3 years we make a lot of networking work, and so we have a connection with a conservatoire, like a place where we are, and university. So also we make a collaboration with Politecnico of Milano, Università di Studi, and other university like Ghent, and of course professional, because also the nice thing that the artists after 1 or 2 years that we are making project, the artists arrive to us to visit our company, and we start talking to each other to make something new, because the artist needs this to communicate with technician, engineer, other designer, to say, I have this idea, but I can't find, for example, in Milan, a place to try to think about my research or new project. And so we thought that was nice to open also this field, this unit that we call pillars in LWT3, the pillars of art and technology. And of course, also the working with the performer, like Davide today. To have an idea, this is the map of our network map of our collaboration in this field. And when I started a week ago, I put some all the collaboration that we have started with Paolo, with Giusy, with Klaas, with Simonetta to the Conservatoire of Milan or Novara, and Salerno, Conservatory of Salerno. We said, but after in this field it's growing. So we are proud to be here, because after working and doing project, we have a critical mass to present. So let's start with some use cases, and the first 2 use cases of the work that we have started with Giusy Caruso in 2019, sorry, and
it's all.
Sometimes the numbers. And this is really, it was really nice, because it was at Milan was the audience was really excited about this work, where you can catch, the audience can catch, and also can at the end of the concert can interact with the composer and the pianist in real time. And the engagement, we start thinking about this word that all of you talk about, the engagement of the public, the engagement of the audience. And from the other side, on the right, is another nice work where Giusy can, in an immersive virtual reality, in immersive modality, can interact with another avatar that play another piano. And this is also was our first concept in the metaverse, and also the audience in that case was really surprised and was really interested about this new approach to make a concert. And these are the 2 other examples of the use case. One is quite similar to the work that I saw this morning. So this is the name is Off Axis. It's the work of this choreographer near Milan in Pavia, Carolina Hanel, where to understand he wants to understand the skills about to move the axis, the body of mass outside. And it was nice also to work with this dancer in the lab, but it's a standard work in our opinion. And then we move also with another work that we presented last year, that is music calligraphy, the work with the calligrapher Silvio Ferragina, that have made this study about calligrapher and also with sounds. So he divided all the characters during the performance. He made this sign. Each sign is a sound, and at the end you can create a little poem of music. So music and calligraphy. The latest two that I want to show are two examples. From one side, this work that we have made using the IoT sensors, low-cost IoT sensors that you can manage in an easy way, also for the artist, and also can make possible for when you don't have so much money to spend about technology, but because this is also a big problem when the artist asks to use this kind of technology. And for example, we can use all the technology that are inside these IoT sensors to make a performance. We can think about in this case, we put the sensor at the end of the bow of the violinist, and you can make a trigger using a max patch to manage this data. And from the other side is a study, is a thesis, master degree thesis of in this case cello. Is a cello, playing cello, and what's happened? We use we use this technology that we usually use for athletes, so biomechanical software, and we made a protocol for the musician. So we move from one field to another field. And this was nice. It's nice work to understand the effort of the shoulder during the playing this cello. And now I ask to Paolo to introduce our big project in work that is a wearable system, and also we have the prototype here that is the state of the art, and also later, if you want, also check how it works, or if you have questions, you can ask me or to Paolo. So that is Wings, the name of the project.
Yeah, just in very few words, this is the project we are working on. We are working on a system, a reconfigurable, tailor-made AMG system that is able to capture muscle activation in different parts of the body. For example, the cello players, okay, you see before, we are studying, for example, infraspinatus or latissimus dorsi or lower back, so different muscle, just to understand which type of effort and fatigue the player. And for example, we have noticed that we have no problem by deltoids or infraspinatus because it's cello players, but she had problem about the core. After 1-2 hours of playing, starting to have a lower back pain because it's very strong muscle from the deltoids, from the infraspinatus, but is a lack of strength about the core. So in other words, she has to make some exercise in the gym to play better. And for this reason, we're starting to think about a system like that. This is, in other words, this is a EMG sensor suite. We are focusing on electronics that is able to capture the data from different parts of the body, because obviously if you play drums, piano, or cellos, etc., you need to understand different muscular groups. You need to understand different patterns for different muscles. And in this way, we are trying to develop a system that is able to be reconfigurable. Okay, we have like we like a tailor. We put the same electronics and make different suite in order to capture information from different parts of the body. And we put an accelerometer and other sensors inside the analog front end in order to capture not only EMG, but we can retrieve information from blood pressure, respiration, etc., etc. As Samuele said, for us at the moment, the electromyography is the thing is sense information.
Why we are showing this? Because we are, for example, this prototype that we have the tank top and the pants is a knitted product. So all the roots because every single roots have a cable inside that is elastic cable with a conductive cable, and it's quite comfortable. In fact, also
class
make some tests at our lab with the, for example, with the pens, and our idea is also to, for dancer, for example, and this was the reason because class came to our lab to find, because this is our method, to find the right muscles that he wants to map, and then we can create in our lab a cut and sew prototype to make this possible. So to acquire not only the inverse kinematics of class, but also the muscle activation. For example, when class it moves really slowly and make a really powerful contraction, the audience is not involved in this loop because it doesn't understand anything. But if we can visualize this data of this gesture and this contraction, I think that it could be interesting for the audience to understand what is happening. And only to finish this part, we have a proprietary software where we can manage all of this data. That is, I told you before, but we can put in sync muscles and motion capture data together. And this is, and we can make some extraction, feature extraction from this raw data. And we are always developing and changing algorithms and put more features on it. For example, if we have a cardio band on an artist or a pianist, we can also acquire that data from third-party sensors. And let me finish with the to introduce the two talent research and musician that are here with us. Davide Leonetti and Roberto Alessandri. And there are two works, but that is bricks of the same project, because we are always have this methodology. We try to find a project that was a brick, and then we can construct the wall.
The brick of the same brick.
the wall together. And from the left, Davide explained better than me his work, and also there is the live demonstration of what has happened about his performance, and also from the other side is the work of Roberto, that is the part of that I told before about the graphical representation of this data in real time. But also he made some tests also with the data offline. That is interesting, in my opinion, because if you have the data, so we work with class at our lab, we acquire a huge amount of data and the information from that acquisitions, and also we can use offline this data to try to analyze the data, talk to class, understand something more in detail about. We can make conflicts also, some conflicts together, and then we can carry on. But us in our lab and class here in Antwerp. And then we can put together the work in a second time. So, carry on, Roberto.
So today I'm going to present a case study that consists in the visualization of biometric data, in particular the superficial EMG, electromyography. So let me introduce myself. My name is Roberto Alessandri, and I have a bachelor in management, economics, and industrial engineering, and I also produce electronic music. Currently, I'm ending my Master of Science in Music and Acoustic Engineering with a thesis on multi-zone sound field synthesis, based on deep learning, and I'm working as a prototyping assistant here for LWT3. And in the future, here this summer, I'm going to be in Antwerp to work for NOSTRI in a project that consists in sound source localization and speech enhancement. So, as I told you, my project consists in finding an artistic way to represent the superficial electromyography, but it's important to understand why we could use it's important for artistic research to use this information. Many times when you see some installation or some artistic piece, what you see is that usually it's used the kinematic to have some effects or something, some visuals or whatever. But there is also much more that is happening. For example, if I want to, I don't know, lift this thing, I could fail, but my muscles are really trying to move this table. And this is some information that we lose. Or also if I lift my arm, there is the first movement when I'm steady, the deltoid is working, and this information could be used in many interesting ways. So this is where I place inside the company. So there is all the electronic part that Samuele and Paul already explained. So my part is in the usage of a native software of LWT3 that is called raw power that I'm going to explain later. And I do a big part of acquisition, analysis, data processing also with Davide, that we fight a lot also, like Samuele said. And there is the process, the visualization part, the last part, that I'm doing alone. So, so here you can see the electronic part, the hardware. There is the electronic board that we use. Actually, this is the first prototype. It's not the one that is going to be in the suit. And the electrodes that touch that we use for our purpose. And you can see some screens that represent the raw power, our native software, that allow us to build a sort of profile of a person, choose some muscles, actually 8 channels for now. And then we have raw data visualization in real time, just raw data with no processing. And when we need to do some artistic research, some artistic application, it's important to choose the right features for our purpose. And we conveyed that actually the activation and the fatigue could be the two more interesting things to use. And in our analysis, after a lot of tests, a lot of pains, we actually, in the end, decided to use the zero crossing for the activation of the muscle, and then MNF, that stands for mean frequency, to study the fatigue. Also, the spectrum is useful. It's not as much specific as the other two, but can be used in both cases. And so, in our analysis, in our project, what we did was to introduce, to integrate actually raw power, the input software with the open sound control protocol. And this allows us to send this information, the extracted feature, to a neural network that we train in order to modulate to some parameters, some values that we wanted to change inside our game engine or graphic engine or whatever we want to use. And then, of course, there is an empirical evaluation to say if we like it or not, whatever is happening. So it's a cycle that repeats until we like it. For our experiments, what we use is Touch Designer and Unity, because I think there are two really powerful tools, much used in nowadays experiments in research and installations. Touch Designer is a graphic engine, and while Unity it's more a game engine, and it's very used for also virtual reality. So here you can see some of the experiments that we did with the control of the muscular activation. And what you'll be seeing actually is the activation of the abdominals of class. And there are 3 kinds of traits. One is going to be almost invisible, and the one on the top right, and it's going to have an acceleration with the tail once there is an activation. Then the one in the bottom left, actually it's a kind of tunnel going in the z-axis, and there is a constant activation, as you can see. It's a really brief one. And the one in the top, in the bottom right, it's a sort of squares. The traits are moving in squares, and when there is the activation, they're gonna start pulsing. So I'm gonna make them start all together, and I hope you see. Actually, here is going another part. Okay, and here. Okay, I think you've seen the traits over there in the top right part, and now in the bottom right there is the pulse that was actually the activation of the muscles inside in the abdominals of glass. And okay, so this is the pipeline that we use for the offline experiments. So what we did was to do the acquisition, the analysis that I talked before, and then after we exported the data and we converted for the offline experiments, we converted to some sound files. Wow, really useful to use, and we divided in subband. We used each subband to modulate the amplitude of each trait, and these traits are moving in an interactive phyllotaxis way. Phyllotaxis is just a spiral behavior that you can find frequently in many plants in the distribution of the leaves, and it's sometimes used for artistic purposes. And here you can see one of the other experiments, one where you can see it better. Okay, here the traits are not moving at all. This was actually a very good acquisition. And in the moment where you will see very well here, the moment where the class is doing the movement, there is actually an acceleration and a trail activation. That we represent one of the rawest things one of the less elaborated actually. You can see some, we also did some experiment with the OptiTrack. We wanted to integrate all the muscular activation together with the kinematics, because even if we want to, we would like to use both together. And so we used Unity also in this case to control some avatars, and actually I think it's really useful when you want to move in an environment without the need of wearing an Oculus, because if you don't have a very large space, like could be this room, when you try to move the Oculus, you're going to break something inside the room. And well, this is the audio of me talking. Okay. So the video is the same, and here is representing actually the pipeline that is happening inside this experiment. In this experiment, we were trying to control also the fatigue, and that's actually, you can imagine that it's a hard experiment to try to convey the fatigue information, because it requires a lot of time. You need to be tired, and when you did a test, it's really hard to do the second one because you're already tired. And so there is the top part that consists in the kinematic acquisition, and we transmit all the data to Unity to the NAT protocol. And the lower part is the same explained before, that from raw power we send the information to Unity to the OSC protocol. And the neural network that we use for this prototype was a simple network provided by Wikimedia. And here you can see the second engine that we provide, Touch Designer. In this experiment, we got to control noisy movement of a particle system, and you will see that I'm going to lift some weights, and this was the first test I did. I lift some weights, and this particle system starts to become very, very, very noisy. This was one of the first one, and we did also the same experiment with some offline information. So again, all the processing, the conversion into a sound file, and here you can also hear the sound file that should represent the abdominals activation. And I think you already see it, but once class is doing the abdominal movement, the particle system is going to become very noisy. Here we go. In fact, activation of the abdominals. And here there is the pipeline of this test. So the raw power fact doesn't change. What we did was to convert this sound file into a spectrum. Then we used a few noise objects, actually. Noise objects inside Unity are very complex objects, but really powerful. And we did a frequency band to color band conversion. Then we converted this color band into channels, and we use this each channel to instantiate a cube. And so at the end, this was the conclusion of my project. We built a framework for an artistic representation of SMG data. It could be Unity, Touch Designer, whatever you like, as long as you receive OSC data. And we also built a template for Unity for the usage with multiple sources like raw power, OptiTrack, and also kinematic sensors. And in a future development, we consist in the addition of many kinematic sensors to like bracelets that we have from LWT3 that will be used to send information inside Unity to represent the spectator and make them interact together with the artist. Thank you. And now.
Finally, time has come. I want to introduce myself again. I don't want to speak with the microphone if I can. I love speaking with the microphone.
Because you're a singer.
I'm a singer, yeah. I don't want to say that. Okay. So, nice to meet you. I'm going to present another case of study of LWT3. I'm the more artistic side of LWT3, can I say that? Without create any other fights. I'm going to present myself very quickly. So I start with a bachelor degree in IT information, and it was very boring. But I did it only for one purpose, for keep going with my master in music. So it was the beginning of my travel to merge the art with the science. That's what I wanted in my life. I'm also a musician, and I'm studying the Master of Science of Music and Acoustic Engineer. That's the good Roberto. I'm doing my thesis, and well, this is my thesis. I'm doing my thesis with the LWT3. And I'm also a composer, a songwriter, and a street artist. So I'm trying to develop something that I can use actually during my performance. And in the future, I'm looking for occasion for merging these two sides as a PhD student or a researcher in some field. So coming to my introduction, what I want to do at the beginning of this internship was try to find a way to create an embodiment of myself during the performance, during playing the guitar. I'm doing the demonstration in some minutes. So then to introduce my job, I want to say that I'm trying to find a new medium for the artist that could be a guitarist or a pianist as Giusy to interact with the effects of your instruments simply by moving, by gesture, that are triggered by this type of sensor that are LWT3 made and developed. So all my job is concerning the way of mapping this very difficult to map sensor, the signal, the muscle signal, very low in amplitude and very noisy. And I'm trying to give it a shape as an artistic mean. So I try to convey more my artistic intention through this sensor and through my movements. So let's present the artistic goal that I put in my mind, because it's like that I'm an artist from one side and then the engineer of the same thing. So I will speak as a two-person in one. So this is my artistic goal. I want to create a new interaction method, as I told you, but I want to be more creative, and I want to create a creativity enhancement. So I try to develop during the project multiple soundscape that I can use and I can trigger with my muscle, and I want to associating some soundscape with some intention, like I'm happy, I'm frenetic, I'm heavy, and then I created then some presets that I can use during my live set. And furthermore, I can control these presets with my muscular activation and the RMS, then I will explain this mode. So this is my 3 artistic goals. And then there is the scientific goal also, because we are studying at engineering, and I have to give also an artistic goal, scientific goal. In my opinion, I will be only an artist, but I love to merge this together. So the scientific goal is for the first time, we try to map all the body of MEG. Based on what I know, all the literature of this field, for example, all the study of Tanaka that we also speak with, is based on 4R. So the technology that Giusy Caruso, for example, uses, the gesture interface, are based on 4R only. We try, thanks to the LWT3 technology, to expand to all the muscle. This is a very good starting point to create a novelty in the scientific field. Then we, of course, have to do all the data model design, to take the data, to pack that, you use the network, the OSHC network, as the colleagues explained. And then we do a feature extraction and a muscle selection based on the artist, or at least the guitarist, okay? And we integrate everything with a well-known sound programming language. This is Max MSP that everybody know here, I think so. So the artist can use it in a very freely way. So very I try to be fast. My system needs 3 types of input from the artist. the artists have to create a gestural vocabulary that's used during the performance. In my case, I create some gestural vocabulary based on techniques that I use, like arpeggio, strumming, pull-off, hammer-on, bending, because I'm a guitarist. These gestures are associated to the preset that I told you before, that the artists have to create in Max MSAP, and he also has to give to the presets a tag. Like it is tagged to which emotion do you want to convey with this type of technique that you play. If I play arpeggio, I want the sound to be more calm, more relaxed. So I said to the machine learning, that this is tagged with relax, for example. And then, of course, you have to give me which kind of effect you want. So virtual instruments, in my case, was reverb, delay, chorus, and distortion. This is a quick architecture of all the pipeline of the signal. So there we have the. Oh, do you see the pointer? Right? No, you don't see it. Okay, nice. So the signal was acquired to this kind of sensors. And it was pre-filtered by this machine board that I have here. And then there is raw power software that all the other colleagues of me present. Then there is the most important thing, that is how we interpret the muscular signal to give us the name. Like, this is my muscular signal to be happy, this is my muscular signal to be frenetic, etc., etc. This is the machine learning part. In this kind of research that we are keeping going, is not finished, it's only the beginning. I use two models of interactive machine learning. The first is to recognize your intention. So do you want the sound to be happy? Do you want the sound to be frenetic, etc., etc.? And the second is regression. It's done by an artificial intelligence perceptual neural network with 3 layers and 24 inputs per layer. And it's modeled the live intention of the musician. So if the musician plays the calm side, but he wants to be more energetic in this side, he can modulate this preset in real time. Okay? So let's go with muscle selection. This is a very important part for the classification. So if you want to have a good classification, you can't take any muscle. All the muscles are very different, and based on what you want to classify, if you are a pianist, you are a guitarist, you are a violinist, you should choose different muscle. So we did a lot of acquisition, and we end up with selection with a selection criterion based on a combination of two features: the zero crossing rate and the mean absolute value. We define the threshold, and we take 12 muscles to test, all the muscle of the upper limb. All of the upper limb, because the other muscle is not related with guitar movement. So based on that selection criteria, that if you want to ask me question more technical, I can answer to each question. Now I try to be speedy to remain the time. So we define this criteria, and then we define these 8 muscles that you can see that I have in my here are the best. So the 2 biceps are very, very important to track like strumming or bending, and then there is of course the part of the upper limbs that is also studied by a lot of other studies. But the biceps are very useful to classify some kind of techniques for us, like bending, as I told you, and also the deltoid is used also because if you want to modulate the sound by other movements rather than playing, you can use the deltoids to move, because the deltoid moves the elbow, the shoulder. And you can kind of modulate the sound also doing this. This is our H peak. So, to have a better understanding of our machine about the signal, these are very weak. We do also a real-time pre-processing. We apply a Butterworth bandpass filter to reduce the noise of the movement, because when I move, all these cables become like an antennas, and the signal start to grow, and my machine doesn't understand anymore what is going on, because I train it with very, very peculiar signal, very clean signal. Okay? So this is the last slide, then with the performance. I want to explain only in a quick detail how the signal goes and the interactive machine learning is presented also with the max patch focus. Okay? So we have these two regression and regression and gestural recognition machine learning model, and it received via OSC the muscular signal. Then there is the max patch that receive the output of the regression and the output of the gestural recognition. The output of the regression is connected to some kind of parameter that I want to map in real time. I want to map the distortion and the delay space, the delay millisecond or the reverber space. So I create two outputs, one for the reverber space and one for the distortion, for example. And the gestural recognition output is like happy, frenetic, and it's the output of the intention that is being recognized. Okay? After that, there is the unpacking, some spike removal, and the sonic preset choose. So there is a preset object, and whenever the gestural recognition decides that is happy, the happy preset is activated. Then there is the parameter mapping, of course. Then there is the external OST that the artist choose. That's me. And then there is a very important part. This is the interactive machine learning part, because interactive machine learning is a technique. It's very important technique for us artists that allow us to train the model based on our taste. So I give the example to the model. I don't want to take training data that is not mine, that I don't know what this is. I give the example to the model, and I say to the model what to do with that. And with this feedback loop, I can keep going, saying to the network what I want, and receiving the sound in real time, and I say, okay, I don't want this happy or frenetic preset to be like that. I can change the preset, or I can change the parameter of the regression is not working. This is interactive machine learning. Okay? So now it's time for the demo.
So you can start.
Okay, I'm gonna start to connect everything.
Yes.
If you have some questions,
I can moderate. So in the meanwhile, you can put up because we are already. So if there are questions, Paolo and Sam and Roberto can answer. Please come here. So.
On one of your slides, I saw high precision measurements that you can perform. What is the discriminatory power that you can measure?
From EMG, depends the type of people that you have sensorized. For example, if you have put sensors and electropads on very high and fat people, it's difficult to have a good precision. The system, the hardware is able to capture data with 22 bits of precision power ADC system. But obviously the precision and the quality of data changes related to the person, the people that you put to the sensor. But in general we have 22 bits of precision of the analog digital converter.
And so you saw medical applications of your technique?
Yes, at the beginning, we have in mind even the beginning the medical application, but just to be honest, the certification path to be a medical application is very long. We are thinking about it, but we now focus. We are focusing on sport and musician, but why not, obviously? But the certification is long and expensive.
And the system is patented.
Okay.
You say before someone says that when you collect data from this system, you can use it not only in real time but also collect data and then after to manipulate them. The question is, because I am composer too and I work with you at the beginning, and I want to know why. With which software you can manipulate this data not in real time? More software, one software, and so on.
And it depends what you want, what you intend to, when you say manipulate.
Manipulate, for
Because
example,
for me, manipulate is to clean the data,
to use it,
prepare the data, and use the data with another software.
for me, is
Or
use the
another
data
platform.
not for a software, but for example, for playing, as explained David before, or to compose something. For example, you keep data from the arm muscle, and you want to compose something who has a relationship with the arm.
We can export from raw power software,
and which software
the raw
to
data, and you can import in other software like MATLAB, and also you can make some analysis or interpretation.
You know,
of the data.
the storage of the data for us is always a database platform.
Okay.
And you have like CSV, XML, JSON,
You have developed
different type of
You
data,
have just
different format
developed
of
it.
data, but yes, you can export everything
you
every
have,
way you want.
okay.
Or you can go to your data and replay yourself with your data that you have recorded before.
That is interesting, because if you want to use the data again, not only in scientific way for measurement, or creative, artistic, for artistic research, is interesting how you can store and utilize that.
We have the demonstration and also performance by Davide Leonetti.
Yes.
Okay, thank you.
I want to show you the output, also the visual output of our software. So I'm now going to show you the 8-channel live plot of my muscle right now. This is the output of my muscle right now. Let's see all together. Okay. So as you can see, we apply a lot of pre-processing for try to remove the movement, because only by moving I do a lot of noise. I add a lot of noise, and that was a very real problem to like try to understand the behavior of a signal if there is a lot of movement. So we apply some pre-filtering, and if I stay like put, okay, you can see that the signal are close to the zero baseline. Okay? Based on that, let's hear some. It's like a demonstration more than performance. I want to demonstrate with you how can we apply this. This now, I want to show you also the patch, because it's nice. So, right now, depending on the position of the room, I receiving some noise, so sometimes it makes me a bit of confusion of recognizing my real intention. But this is like the intention of calm, because it's applied to page.